what was probably the best talk of the day, I'm sure. But since I've already heard it, and the credit for that all goes to not his supervisor, but his manager, I think. In any case. So now, next session. Before I introduce the speaker, I have to introduce a very, very, very special, distinguished, honored, privileged guest. Come, Tom. So for many of you who are, come here. Come to the front, please. For many of you who are in the younger generation, which most of you are compared to most of us, Tom Binford, if you don't know this name, you probably have to go back and re-educate yourself on computer vision. He is one of the original computer vision researchers, dating back to before time, I think, as far as I know. And was, literally, you think of some people and you talk about some institution as the fountain or the spring, from which lots of things came out. And in Tom's case, it's exactly true. I think for the first, from the middle of the 70s to sometime in the 90s, probably some of the best PhDs and faculty in computer vision that came out were all Tom students. Right? And he's been a springboard of any number of research ideas. And amazingly, I don't think he ever held a regular faculty position at Stanford. He was always like a research professor with his own funding, and all kinds of great students came out of it. He's Alyosha's academic grandfather actually. Jitendra Malik was a student. Let's see, Rodney Brooks was a student, I think. And,
Rujena.
Who?
Rujena
Baichi was a
David
student.
Lowe.
You know the names? Yeah, I mentioned it. So who else? They mentioned a few of them. Who else was a student?
Who was?
Who else? But the most important was the first student. The reason I mention all this is because Tom Binford's first PhD student is right here. Ram Nevatia, who's our next speaker, thank you, Tom, is actually Tom Binford's first PhD student. And after doing his PhD, he went to, I think you've been at USC ever since then, right?
Ever since then.
And of course, Ram himself is one of the leaders of the field, an example of the kind of people that came out. So Ram's been doing recognition, modeling, image understanding. I think he's seen all the different waves, starting from the old IU wave to the surveillance and security wave, and gone through several generations of recognition ideas. And people, when they think everything works today, he probably grimaces a bit or something like that. Well, I've seen this before. But without further ado.
Thank you. I think I have another microphone. So thanks to Anand and Manik for inviting me.
I have to. One thing I forgot to mention but most of you would be surprised to know this. Tom now has been a Bangalore resident for the last 8 years. Okay, so.
Yeah. So anyway, thanks for inviting me and all the people who did the organization. I had no idea what kind of audience I was going to have. I assumed there were 8 invited speakers. There will be going to be 8 of us plus 2 or 3 other people sitting around the table talking about what was new, philosophy and so on. So I originally started to organize my talk to impress those people who had heard me talk before, like AZ, Anandan, and so on, so that he wouldn't say, I've heard this before. But I realized that many of you haven't heard me talk before, may have read my papers, but at least haven't seen me in person. So I tried to give a little bit more of the broad view rather than what did I do last 6 months. So activity recognition presented by Andrew. I think you've done a lot of the spade work already as to why we should do it, what various approaches are. What I present will be slightly different in style. So why do we want to recognize activities? Obviously, if you have a video, it is one of the key aspects of the content. If you go and see a movie and want to describe to your friends what the movie was about, basically you talk about what happened there. You don't remember the pixels and colors in them and so on. Practical reasons, monitoring, that's security kind of monitoring. You want to have alerts. Something bad is likely to happen, might have happened. Indexing, which could be for forensic or deep analysis, something after something has happened, like London subway bombings. You want to go back and get the relevant data, or it's just a more generalized version of the indexing problem that Manik talked about. If we do it through the video, if we can get the events in it, life will be a lot easier. Human-computer interaction, a whole bunch of things. I just added this one bullet. This is not a motivation, but just a piece of information may not be commonly known, that 2 major new research projects that emphasize activity recognition have started in the US, one called MindSci, sponsored by DARPA, another one called Aladdin, sponsored by IARPA. One is first one is more for robotics type of applications, second one more for indexing type of applications. Search through YouTube for relevant videos. I'm fortunate to have a role to play in both. Otherwise, wouldn't have mentioned it.
What is IARPA?
IARPA is the ARPA, the Advanced Research Projects for the so-called intelligence community. So they worry about
Spooks.
Yes, spooks. What's hard about activity recognition? Andrew again has introduced this. All the problems of 2D image analysis come in. Variations due to viewpoint, due to illumination, texture. In addition, we have variation style, the same action performed by different people, not the same, or by the same person at a different time is not exactly the same. I don't know why this thing jumps twice in a row. Maybe work with this. The problem with these 2-screen things is you can't point. You need 2 pointers. That's a vision problem. Somebody points somewhere, projected on all the screens. I want to emphasize this problem, temporal segmentation. I think it came up in Andrew's talk also. Most of the work in activity recognition assumes that somebody gives you a clip. There's only one action in it, and you classify it. Whereas in real life, data is coming in a stream, and you need to detect the events, not just classify the events. So detection, as we know, is a much harder problem than just classification. Also, people talk to me about recognition of novel events, not just things that you know about, drinking, smoking, waving, pointing, and so on. They want to know things that don't have a name, but we need to recognize them. Not quite sure how to do it. I may conclude on some thoughts about it, but mostly I will talk about events that are not novel, events for which we have models. So possible approaches, I want to go through this relatively fast. Simplest approach is we have a video sample, we just match the 2 signals directly. There may be variations in scale, especially in time. So there are techniques called dynamic time warping and many variations of it. I'll say no more about that. The second common approach, a very dominant approach, is this one. You extract some kind of spatio-temporal features. You collect them in some way, typically a bag of words, or more common. More recently, people have proposed clouds of features. I think the earliest work was done by Ivan Laptev on this. There may be others that I'm not aware of. This is mostly done as a classification task, not a detection task, though he and others have been trying to generalize that. And Andrew introduced a nice variation where some use is made of localization and tracking. In the classical version of it, you just take the whole volume, but you can get better performance, obviously, if you take some advantage of finding where people are. I'm going to go one step farther on this, maybe many steps farther along, maybe too many steps farther along that line of thought, and follow a structural approach. And what the structural approach means you will see in a moment, but what I really mean is that we need to find objects, we need to track them, we need to find what the relationships between them are. essentially understand the structure of the activity, not just some features associated with that activity in a global sense. This approach has many attractive features, also has some serious problems that if we're going to find the structure of the activity, if we're going to recognize based on the structure of the activity, we have to first find that structure. And finding the structure is not easy. Even finding people in videos is not easy. So I want to introduce this notion of event hierarchy. And start by defining something called a composite event. If you go out for dinner, what does that consist of? If you're at your home, you need to find some transportation, you need to make a reservation, you need to call your friends, you go there, you look at the menu, you order the food, you eat, etc. All this could be called, we went out for dinner. So it's natural to think about this activity as consisting of these components, and they have some order to them, rather than saying, I just find some features of this video and do a histogram. The composition is usually, but not necessarily a sequence. A happens, then B happens, then C happens. And there are multiple actors. Several things could be happening simultaneously, and some spatio-temporal relations between them must be satisfied. It seems to me that events in everyday life form a natural hierarchy. It's not strictly a tree type of hierarchy. It may be a lattice. Some events are shared by other higher level events. I do this definition in kind of a reverse order, maybe more natural to talk about a primitive event first. A primitive event is one that you either can't break down or don't want to break down anymore. So walking in the context of going to dinner might be considered a primitive event. If you're doing gait analysis, then you can talk about left leg forward, right leg forward. At some level, you can talk about neurons firing or electrons changing state or whatever. Everything can be decomposed. So I say we choose not to decompose. And these kinds of actions, we have to recognize from some video property. And that maybe bag of features is one of the possible approaches to that. There's a very natural relationship between these composite events and graphical models, such as hidden Markov models or conditional random fields, because these models essentially consist of states and relations between the states, temporal relations between the states, which correspond to a sequence of events. I think I'm going to skip that slide. So without going through the details of this, this is a typical hidden Markov model. It says for some event 1 happens, then 2 happens. In the end event n happens. If you traverse the whole chain, we can say this larger event has taken place. How do we know whether event 1 has taken place or not? There are some observations we can make about it if that's happening, like if I'm waving my hand, there are some features that you can observe. CRFs are a more modern variation of the hidden Markov model, and probably not the right time for me to go through the details of that. In video, as in many signal processing problems, there is a lot of uncertainty. We have some observation. Those could come from event 1 or 2 or 3. We're not completely sure. We can get some kind of a probability distribution. We have a sequence of observations. We want to find a sequence of states, in particular the so-called most likely state sequence, which is given by typically a Viterbi algorithm. I like to always mention this because our school is called Viterbi School of Engineering, with a V there. I've asked the school to give me some funding every time I use the name Viterbi, but
every time it's a new funding they have to give you.
They should give me some, yes.
$10 every time.
$1,000 or something, $1 million. Let me skip this too. I want to divide the world of activities into 2 classes. You can divide it into many different classes. But for today, let's just talk about mid-range and near-range. Mid-range is like 20 meters away, where you can see cars, people moving around, and whatever you're trying to make inferences of, you can do without seeing details of the human body. Like somebody's getting into the car, somebody goes into a building, two people collide, they meet. Near range is gestural kinds of things like waving hands, pointing, whatever your examples were, drinking, smoking, kissing. These require you to have some idea of the pose if you're going to follow the structural approach, or you just have a bag of features. This computer has a mind of its own, all right? Some of you who know me probably have watched this 500 times. Please excuse me for that. I was not going to play it for you. Okay, what happened here? Anybody? In that video, if you were watching it? Left a bag. Okay, so here's the outputs of our system. It says at a certain frame, a drop-off event happened, then a warning happened, which is defined to be a certain distance away from the bag, and then an alarm, which is defined to be a certain time also. These rules are provided. This is not the focus of my talk today. I just want to show that these types of activities, which I call mid-range activities, they can be done relatively easily if you can do tracking of the people and the related objects in a clean way. And Andrew told us no problem, right? In very crowded scenes, this is not straightforward. This is data of Gatwick Airport in UK provided by commonly available data. We're trying to find two people meeting. So here, two people come to meet. I showed this video only to indicate that, I'll freeze it here, that just tracking of people in very crowded environments where there's a lot of crossings is not an easy thing. And in Europe, Andrew, everybody wears black. You're the only one who does not wearing black clothes. So appearance doesn't help directly. We have a lot of very interesting work on human detection and tracking. We think we have some of the best technology to do that. That is not the purpose of my talk today. If you're interested, talk to me afterwards. What I really want to talk about are these close range activity recognition, where the knowledge of pose is needed. And again, Andrew showed us some results of pose estimation just from a single frame. Many people work on that, including people in my lab, but those methods are not very robust. They are very slow. Some of the methods may take minutes per frame and then get the wrong result. Or people use multiple cameras, 6, 8 cameras, so that all the reasoning can be done in 3D. That's also not possible for many applications. So I'm going to talk about a top-down approach. By top-down approach, what I mean is that we have a set of activities like waving hands, pointing, kicking, and so on. At each time, we're going to evaluate whether one of these activities is happening, whether actually evaluate probability of each of these activities. And I've invented this term, but nobody else seems to follow it. In robotics, there is this popular slam, simultaneous localization and mapping. So I call it simultaneous tracking and action recognition. Would be nice if you could do the pose tracking first, then the action recognition becomes easier. But in this approach, the tracking will be kind of a side effect of recognizing the activity. Current work limited to single actor actions, the close range one. The mid-range actions we do with many, many people. Here's another data set. Andrew, this is the actorGÇÖs. I always confuse my data sets. You don't know this one. Okay? So Also, as Andrew had pointed out earlier, it's possible that we can just look at one frame and see what's happening, though sometimes I just have to breathe on this one. Okay, let me go back. So during some interval, check watch is happening, then punch happening, kick is happening as a continuous stream. We need to segment the video and give it a name. In addition, we want to find the 3D poses that correspond to those activities. Don't have to if your only interest is in finding activity recognition. You can see it's the same actor. They film it from 4 different viewpoints. The videos look quite different. You can combine the 4. In my case, I'm not combining the 4. I take any one of those 4 views. Other variations I don't have time to show you. So I'm having a very sensitive laptop and also a very sensitive remote. I want to use the word key too many times. I mean, this is the key idea of key poses. Okay, that activities can be described as a sequence of some key poses. For walking, there are 5 of them. If I put the pointer there, I'm afraid this slide is going to change. Where for sitting, there's only 3. For standing, it's the same 3, but in a different order. And in a graphical model, we represent the walking action with these 5 sequences. This is an HMM-like structure or some other variation of a graphical model. We can switch from one action to another. In this particular implementation, we assume that you can only change activity after you've finished one of them. So if you're going to sit down, all of a sudden you can't run if you're in the process of halfway crouching. These key poses could be decided by a person or they could be inferred automatically. One key idea that is not on the slide is that these models exist in 3D. We acquire them from motion capture. Our observations are not in 3D. We have to match the observation with the model. I'll get to that in a moment. The number of key poses turns out to be not so large, surprisingly, at least to me. We had 15 different action models, and we find only 177 key poses. There are still 6,372 nodes in that network because.
So these 177 are found automatically?
These are found automatically, yes.
Which local data set are you?
Talk about the need about getting away from motion capture data and trying to get these action models directly from videos, if I get that far. The way the matching between 3D and 2D happens, it's sort of a crude method, but that's what it is. The tilt angles we assume are in a small range. For surveillance videos, typically the cameras are looking down at an angle of 15, 20, 30 degrees. But we don't know which orientation the person is going to be relative to the camera. So for each pan angle, we create a 2D model from the 3D model that we have. One for 0 degrees, one for 10 degrees, and also we allow people to do some amount of rotation during the action. Again, the details of this model are not exactly important for getting the big picture. There's some meaning to those colors that I will not describe to you. Here's the data set, some frames from the data set. There are 50 clips, 5 different viewpoints. Again, we do not combine. Most results on this data set are by combining the 5 viewpoints. We do each viewpoint separately. There are 10 actors, 5 males, 5 females, so it's a fairly rich data set. Still relatively clean background. So background subtraction works. In fact, with this data set, I believe they provide the background subtraction. It's not perfect. It does have errors. Okay, let me stop this. want you to watch this video carefully. It will test your watching skills because there are too many things going on at the same time.
What's the video watching?
Here is the original video. Here is the final result. At the bottom will be the label of the action that's taking place and also some estimate of the 3D pose. Over here is going to be the background subtracted or the foreground. And here is going to be a result if you were only looking at one frame rather than looking at the whole sequence.
Just the action net is what?
Yeah, I should have described that. So let's go back. So this is the action net. The whole model consists of a graphical model like this. Each segment like this corresponds to one action, this corresponds to another action. Then there is a bunch of viewpoints. I think we quantize to every 10 degrees. So for any given frame, we need to compute the probability of are we in this state, are we in this state, are we in this state, and so on. And for the whole sequence, we want to find the most likely path by using a Viterbi-like search or dynamic programming. 0 to 180, I think. I'm not sure there is a symmetry or not.
And you will have the arcs going from various angles to other angles as well, like total ones.
Yes. But you're not going to do this. And these links are also learned from data. There are too many to design by hand. I should have introduced the word action net. So this is the action net. Yes. What's the criteria? So in the automatic method, it's based on some kind of change in energy, a maximum change of energy defined by how fast the joint angles are changing, and look for peaks in that. In some of our later work, we actually do this by hand. Manually, if we look at some action, it's relatively easy, like waving hand, left extreme, right extreme, maybe the one in the middle. Yeah. In this particular one, they were detected automatically. In some of our newer work, we decided manually.
How do you detect that angle at which the person is?
No, during the construction of the network, that is during the training phase, the key poses are defined then. When we're actually observing an action, we don't have any idea of whether the current pose is a key pose or not. We're computing probability distribution based on the shape. I don't know whether I answered your question or not.
So you're finding the key poses in the training phase, right?
Yes.
And maybe with the distance measure, you will find out.
What we want to do is construct this network. The training consists of deriving this network and the associated observations with each one of these nodes also is a prediction of what you should see in the image. Yeah.
So this network, this is derived from the mocap data or from the visual observation?
This is derived from the mocap data.
Okay. So this is what they call the motion graph. And then you're trying to explain real video with this motion graph, right?
I have not heard the term motion graph, but yes, I call it an action network.
Well, in graphics, when they kind of synthesize how characters walk, they basically kind of sample in this graph.
You could say that. I think in the graphics context, you could make a motion graph which says if you're in this pose, what other pose could you go to next?
That's right.
That's not constrained by activity. This network is constrained by activity.
Okay.
That says you can only be performing one of these 15 actions, and if you're performing one, that's the probability that you will go to the next pose.
Kind of, the graph has these chunks, clusters.
Yeah, absolutely. That's the whole idea.
When you say 177 key poses, so there are 177 key poses in the videos that you consider, the kind of activity you consider? Or
Yes. Yes.
There are only a bunch of different key total of different poses that are.
No, I don't say that, but there are 15 actions. And remember, at the very beginning, I said complex actions can usually be decomposed into simpler ones. Whether the set of simpler ones is 15 or 25, I'm not sure, but I don't think it's hundreds.
So if you have a pose in which, like the one you show at the top, the
Yeah.
person is walking. So the hands are relatively, I mean, they can be in arbitrary positions.
They can be in arbitrary position.
Like different key poses, or they.
They're not, because the hands are
They shouldn't be, right? Because
Yeah.
ultimately what the hand position is irrelevant.
because hand position is irrelevant, but for waving action, the hand position is not irrelevant.
We want to see the results on that elevation.
Okay. So here you can see the results. Stand. Occasionally you'll see flash some mistakes, scratch head, sit down. Wave. A lot of standing, kick. If you see this one, you can see this one changes a lot. Louder, please.
How are the transitions detected from one action to the next? What's the trigger?
There's no trigger. There is a sequence of observations. We're just finding the best path through the network. So at some point, the state in that big action network has part of its descriptor is which action is being performed.
So it means that you have to do a batch optimization,
On the whole network.
No, so one question, I guess, is it causal, right? You want to know if it's causal or...
No.
Is it causal?
No. Think about speech recognition where you have a vocabulary of 1,000 words. So at each time instance, you are trying to fit a model of each one of your 1,000 words. And in continuous speech recognition, there's no pause before you go to the next word. And the pause just happens because...
I think the question, Pascal's question is that you don't have to... You can predict the current action on the basis of the past alone, right? You don't need to process the future in the video. Do you?
No, we do look ahead. Yes, we look at the whole video, then we parse it, we give you the action. Now, if you say, I don't want to wait, my video is 10 hours long, I don't want to wait for 10 hours before I get an answer, really the relevant context is relatively small, so we can also do it through a sliding window of 30 seconds.
You need the future in order to talk about the past.
You don't need it, you will get
Better results.
right? It's a matter of whether you're doing filtering or...
It's batch. Just keeping a window of frames, working with the window of frames, that's all.
Yeah, you could do a sliding window with a latency of a couple of seconds. But sorry, I didn't get that flavor of the question before. So this is work that was done maybe 5 years ago. It's got kind of the basic idea of the approach that we take to activity recognition. Rest of the work is in actually making it work on more complex environments. In the example I showed, the background is relatively simple, and so good results can be obtained more easily. As we go to more complex environments, it's not easy to get foreground segmentation. That's one modification generalization that we have done. Another one is that just looking for key poses is not so satisfactory. So to think about if the key pose is like this and the next one is like that, my hand is in between, to say what's the probability that it's this one or that one, you don't get such good numbers. So we also model the transitions in between. We make that graphical model to have hierarchy, and there are other generalizations which may not make too much sense to you if you're not familiar with graphical models. So I think I'll skip the details of that. The important one I want to mention is a duration model. How many people here know HMMs somewhat well? So in an HMM, you're in some state. What's the probability that you can stay in that state for next 100 time frames? That probability declines exponentially. No matter how low is the probability of transition, eventually the HMM says you got to go to the next state. But if you put duration models, you can modulate that. You can say it's okay for you to be here for 1,000 frames. The cost is that your decoding algorithm, the generalization of Viterbi becomes more expensive. And we want to remove the need for mocap data. So here is a small innovation. Let me play this video, you will like it. Okay, what happened? Like that. This consists of, kind of fun to play, consists of two actions between two key poses, two transitions. So we can represent this action, which actually has some meaning in some signaling, military signaling. I don't know quite what it corresponds to. So it's a composition of two very simple things. Primitive event 1 and primitive event 2. Okay, here it comes in full flavor. So we say a composite events is some high-level event like signal 1, signal 2, signal 3. You can go from one to the next with some probabilities. Each one of these has a sequence of primitive events that take place. We also want to keep track of how long you have been in a certain state. We want to know what pose you have. And at the bottom is some observation. Observation may be optical flow, maybe shape of the foreground blob, maybe some other things that I'll give you details of in a few moments. This is way too, how much details should I give you? I think I'm going to skip the details. Let me just work on this slide a little bit more. Our model for transition, in this method, we also have a model for transition between the key poses. It's basically differences in angles. So we just define a function that says how the joint angles change, typically either by a linear transformation or by some kind of an affine transformation. So when you're making an inference, what you want to know is what action is taking place, what pose am I in, or the actor is in, and how long has the person been in that pose, or how long has that event been going on, not in that pose, but how long has an event been going on, right? So if I'm raising the arm, it's been going on for how many frames, and we want to make an estimate of that also. Maybe I should go through here. Our system has a limitation that we need to start with some neutral pose, and then for each current state, predict the primitive based on current duration. Easier for me to read here. This got more details than I had in mind. So let me simplify. We have this graphical model. We initiate it with some neutral pose. We start the process for every action. There's a prediction. We match the prediction with what we see and compute a probability distribution from that. And there's a lot of details here that are probably not so important. I just should make one point, is that when you are going away from key poses and also looking at intermediate positions and durations, your space is becoming very, very large. It's basically real valued numbers, and you got 50 of them. So we have to resort to some sampling techniques. We cannot compute the probability distribution of all the states. So a lot of these details have to do with how the sampling is done, and there are some examples of what the relationships between the various states are. But this slide might give you an intuitive idea of what's going on. So here is the action at time t-1. Here is it at t. We take differences of two adjacent frames. That's some kind of a approximation of motion. We extract foreground blobs. We have some predictions of what the pose should be. If we assume that a certain action was taking place, there is a prediction. We make prediction for every action. For some, the match will be good. For some, the match will be not so good. And here's some details of actually what gets computed, how the overlap of prediction and the observation take place, and maybe the details of that are also not important for today's talk. Here's the prediction is coming from the 3D model. Here, the observations are coming from the image. The two get matched. So this is one result. Unfortunately, the graphics on this is rather bad. If I can stop it somewhere. That's not a good place to stop. I believe that white is the result of doing the dynamic analysis, and the yellow is the instantaneous analysis. And these white dots are supposed to give you the outline of the detected pose. Nobody can see them.
Detecting the pose within the frame. I mean, not the pose, but the person. Is there a person detector?
Yes, there's a person detector to initialize, but after that is just the tracking.
Oh, I see. So it's background suppression.
It can be background subtraction or not.
Okay.
Right. Once a person has been detected, and then if I'm walking, then there's a prediction of where the person will be. So in one of the variations, we could just compute edges and compute how much distance between the expected edges and the observed edges. For example, so you don't have to do background subtraction.
But basically, you use whatever tracking or algorithm, and then whatever it finds, it's being fed into your pose activity analyzer. Right? It's two separate processes, or is there a feedback loop?
If the person is in an upright pose, what we call a pedestrian, there are some very good pedestrian tracking algorithms, including ours. However, when a person is performing actions where the pose is changing, nobody has a good tracking algorithm. So the tracking is actually done through the process of action recognition. There is not a separate tracking process. Let me skip that too. Let me get to this one. So this work was aimed at going away from the need to have motion capture data to get the 3D action models. We wanted to do that just from one example or two or three examples of video. That's easy to get. Motion capture data is hard. We have to go to CMU or somewhere else, and people have to wear suits. It's a very laborious process. So the idea is that the person looks at the video, decides on what the key poses are, and it's not super important that we get the same key poses. Instead of 3, if you choose 4 or 5, that's fine. From these key poses, we ask people to annotate joint positions in 2D. Knee position, what's this? This is elbow position, head position, and so on. We lift these 2D points to get an approximate 3D pose. So the user gives 2D positions and gives us some ordering, like this one is in front of the other. Based on this information and the human kinematics, it's possible for us to actually get the 3D pose from the 2D pose. Once we have the 3D key poses, we can interpolate in between to say what should be happening in between. And it's done in a somewhat rigorous way. Sorry?
How do you differentiate between primitive 1 and primitive 2?
Um,
I mean, how do you get to know that now these frames will form primitive 1 and these will form primitive 2?
between any two key poses is a primitive.
Any two key poses?
Is a primitive. By definition. Here's one example of, again, it's a little bit more details of how the transition between the two key poses is defined. Basically, a joint and an axis of rotation and the angle. Whoa, let's forget about that one. So this approach was tested on 3 data sets. Andrew, did you mention Weitzman? Okay. So it doesn't matter how good your system is and how complex your data is. If you don't compare it to some standard data sets, which may be ridiculously simple, your paper gets rejected. So always we have. Weitzman data set is the standard data set, came from Weitzman Institute. It shows you what the action recognition accuracy is. There's no ground truth for what the tracking accuracy, the ground truth only consists of the labels, does not consist of various poses, so we can't measure that. Gesture data set is the one that you saw where people are picking up something from the ground, sitting down, and so on. And we collected a rather complex looking video in a grocery store. Somebody goes shopping, picks things from a shelf, and see, the results are the best and the most complex data set.
We have 10 minutes?
10 minutes.
How you want to use it?
Okay, I think I'm going to go fast then. Some representative frames from the Weitzman data set. This is gesture data set. Here's the grocery data set. You can see the background is quite complex, and some of the poses are very, very highly articulated, like crouching down. Let me skip this one also. I'll show you this in the interest of time. The other video actually shows you the process of annotating and deriving the models. If you've not seen Weitzman data set, this is Weitzman data set. You need to try it. Otherwise your paper will be rejected. This is data set that we have collected. Our aim is not to get exact pose, but you can see the pose that's inferred is not so bad.
Do you have any data sets with a moving tail?
We may. We keep trying to make one.
What about this, the Hollywood one?
Let me talk about that towards the end. Please remind me. Our newest work, which I think I also will not have time to show you in any detail, is to add a layer below here. In what I've showed you so far, there's a very strong prediction. We get some kind of a foreground blob or edges and match them. But really, we can see a little bit more in each frame. We can see parts. We can see where the head is. We can see where legs are, where the torso is. We cannot do this reliably enough. We cannot just get a pose from a single frame. You and I can, but our algorithms cannot. So we're meeting this problem halfway, saying we're going to make a prediction of what the pose is, but instead of just matching the boundaries, the prediction is saying where is the head, where is the arm, where is the torso. We have detectors for these parts. Let's apply those detectors and see how good the match is. And since my time was said to be up, I'm going to skip more details, but you can see that this new method called D-band parts, which was presented at ICVGIP, by the way, gives some improvements. And I'll show you the movie. So you may or may not be able to see the difference between this one and the previous one. Is the same data set. The results are a little bit better. There's less noise, and the accuracy of the joint angles is much better. Let me stop this also. Let me get to this summary, and then I answer Alyosha's very important questions. And I don't have a bullet for this. So what I've tried to show you is what I call a structural approach to activity recognition. That is, activities have some kind of a structure. The structure can be at many levels: primitive, primitive, primitive. Within the primitive, there is state, state, state. You can do this at as many levels as is appropriate for the problem. As a result, you get the pose, you know where the person is, you get a description. You don't just get a label. But there are problems in actually finding people. Just initiating the process may be hard. The hierarchical representation reduces complexity. To make these things work really well, I believe the bottleneck is still in getting good descriptions from the data. Just purely top-down approach has some limitations. Not listed here explicitly, should be listed here, is that these methods are making a closed world assumption. It says one of these 15 actions or 5 actions, whatever is your data set, must be happening at each time. If something else is happening, we're going to find one of those 15 as the best fit. We might say the probability is low, the confidence is low, but it's making a closed world assumption. What about the Hollywood data set? Will my method work for the Hollywood data set?
You also want the camera movement?
Camera movements,
Visibility of the bottom part. I mean, without that, the prediction would not. Without it, the prediction will not match.
if the camera is moving?
If you do not model the camera as well.
I'm not sure I'm understanding your... Yeah, it is true that in all the examples here, we have a good model of where the camera is. In the Hollywood data set, we have no idea of where the camera is. What are some other distinctions you would say, Andrew? That is correct. If the camera is moving, background subtractions won't work. So our methods don't necessarily require background to be subtracted. As I said, we can match the edges of the observed body parts. Actually, we have a detector. We have a upper body detector similar to Oxford upper body detector. It will find the upper body regardless of whether the camera is moving or not. That is one of the features. We can disable that feature and not use it at all. Yeah.
So you're predicting and then matching whether you are in which state you are going. So, but if the camera is moving, then the prediction will not necessarily match what you see.
Could be an issue. But I think the biggest difference might be in the Hollywood data set, these actions are quite unstructured. To say hugging can happen in so many different ways.
And there are neutral actions in there as well, isn't there? And I guess the framing.
Well, the neutral actions are still in action. The person is standing, walking, sitting. So there's no undefined actions taking place there. It's not drinking or smoking, but if you generalize your set to include standing, sitting, walking, I think the whole video is included. Sort of the distinction, I think, is the same as for object recognition. There are all these bag-of-words based methods. They can work reasonably well. They have their limitations. There are very structured object recognition methods, which say a human consists of a head, torso, legs, and so on. If the objects are well modeled, the structured approach is going to work better. If you don't have a good model, the structured approach is going to fail almost completely. And I think the same thing applies here for activity recognition. So my current thought is that at the primitive action level, perhaps the bag-of-words kinds of methods have a role to play. But certainly for more complex activities, we should be thinking about representing them as a sequence of actions or a set of actions taking place in certain order. And certainly I'm committed to following that approach. Yeah.
Can you comment on how similar it is and how non-similar it is?
So if you go to Laptev's methods, I would say what I'm doing and what Laptev did are two extremes of a spectrum. I spent a month at INRIA, and I was given an office to share with Ivan. So we ended up not fighting and started to see that the differences were not as sharp as before. But they're basically two ends of the spectrum. I think Andrew brought it closer by saying don't look at the whole spatio-temporal volume. Let's do some tracking. And we know that the action is here. As I said, to my way of thinking, the lowest level primitive action could be done in many different ways. The way Andrew is doing it or Ivan is doing it is one way. But to do a very complicated action like going to dinner by having a global description for it is probably not the right way to do action recognition. And Andrew is nodding, so we agree.
Is there a general method to initiate your action recognition system based on the density of motion? Because if you do observe any action in an object or a person, it's usually based on a motion that you get your transition and different states. So if I'm going to get up, that involves some motion.
So the motion, not just the gross motion, but actually motion flow everywhere is one of the features. It's not used to initiate it. It's used to compute the probability of whether that action is happening or not. Because from our model, we can also predict what the motion of the elbow should be, what the motion of the head should be, and so on. So I didn't spend too much time talking about the lower levels, but at the lowest level, there is a shape match and there is a motion match.
So the algorithm doesn't run all the time, only when there is a threshold.
Algorithm runs all the time. At every time, the algorithm is evaluating every action and every pose of every action. But since the space is too high, we do it through sampling. We cannot afford to actually take every state. So based on some probability distribution, we only look at a subset. Yeah.
Have you done falling action?
We have.
Things that are non-vertical, right? So like horizontal, rolling, falling.
It's kind of tough on the graduate students who have to perform.
No, there's a lot of interest in elder care.
We have
Elder care for monitoring in
But the training data is hard to
the training data.
Well, there's a small story related to this. So we've not done falling action in this framework, but we did make a detector for a person falling down. And actually last week we did a demonstration of this in Korea at Korean Airlines. And we did collect training data by various people falling down. And also during the test, somebody had to fall down. During training, we provided them a pad on which they could fall down. And also gets your clothes dirty and other things.
Another related question is, have you done any of the models where you need, besides the body, you need some other object to do the action, right? Like,
Yeah.
like stairs for walking,
This-
or weightlifting, or all those types of things. Right? Where you're-
This is a great comment. I should have included it on my future work slide. So if I throw a ball, or not that, let's do a pickup. So did I pick up something? I didn't pick up anything. Currently our system is just looking at the mimic actions, but actually we should see the object. If I picked up something, I should see an object. Our new project, the DARPA MindSci, is very much oriented towards interaction of the person and the object. So two natural directions for me to go are interaction with objects as well as deeper interaction between two people, like hugging or shaking hands and such. But as far as I know, almost everybody ignores interaction with objects. But
Hugging and kissing. We can move on to hugging and kissing after this.
Hollywood doesn't provide much funding. So I think Manik has gotten up, means I should sit down.
No, we have a couple of minutes.
Any more questions?
So you said you would talk about data sets.
I did. Oh, why I don't use the Hollywood data set?
And in general, the issues of data sets, right? Because, what the data sets that you are showing, you have graduate students who perform actions.
Yeah.
Andrew has Hollywood movies, which is also not real life, right? So, can you talk about kind of the bias, the data set bias for training versus the real world scenarios where you actually want to test it?
So this is a very serious issue. Either we have these very artificial looking data sets, or we have, I would say Hollywood data sets that are actually quite realistic, even though they're artificial in some sense. I think most of what happens in a Hollywood movie has so many complex actions, it's difficult to model them. It will take a while before we build up to that. The MindSci program has 50 actions that it has selected. They call them verbs. And
They call them what?
verbs. Each action is a verb. And they are creating a data set of something like 50,000 videos. Whether people will find them to be realistic or not is an open issue. They are somewhat artificial looking data sets, but a very large data set is about to descend upon the community. And my understanding is that that data set will be made available to the general community. Currently, it's only available to the contractors in that program, but within a matter of months, it may be available to everybody. But how to find? It's easier to get data sets for object tracking and object recognition because this is happening all the time. For events happen rarely, and bad events happen even more rarely. So how to get the right training data and how to get the right test data for these events of high interest is a real issue. And I don't have any good answer to that.
Also, your application domain are different. For you, it is surveillance monitoring. So you need specific things to do. Add a fixed camera.
Yeah.
His is different entertainment purposes, also some other purposes. You want to pick up data from the movies, for some, how many times person drinking or, doing some actions. So
It's
domain
not,
is different, I think.
it's not so, well, okay, at some level it's different, but for both of us, we really want to understand the science behind it. We want to do activity recognition, solve the general problem. The second program I mentioned, the Aladdin program, which hasn't quite started, its goal is to take something like YouTube, which may have 50,000, whatever is the number posted every day, and say, find me the 10 videos that may be of the most interest to me, and there the environment is completely unconstrained. So, yeah, but